In this assessment, we're asked to draw all internal symmetrical alkynes with the molecular formula C10H18. I've gone ahead and shown a 10-carbon chain so we can get an idea of how this will start. The alkyne needs to be between the central two carbons. And so if we dot it in here, and I'm going to redraw this so that we can have the shape be correct, we see that we have 4 carbons on either side of the alkyne. It is symmetrical. So let's draw the real example of that. 1, 2, 3, 4. 1, 2, 3, 4. 4 carbons on each side plus the 2 alkynes give us 10 carbons. Because the molecular formula is C10H18, we only have 2 degrees of unsaturation, or an index of hydrogen deficiency of 2, so we shouldn't consider any of the rings. That gives us a clue to what we're going to do next. Instead of thinking of these as having 4 carbon chains at the end, let's imagine it as a 3-carbon chain with a methyl group that we can now move around. This will allow us to generate this new structure, so there's a 3-carbon chain and a 3-carbon chain. Only 8 carbons so far, but let's put carbon 9 and carbon 10 as branched groups there. Still symmetrical. We can do the same thing systematically. Let's keep it as our 3-carbon chain on both sides. That's 8 carbons. And now instead of putting the methyl group on the second to last carbons on each side, let's put them at the carbon directly attached to the alkyne. 1, 2, 3, 4, 1, 2, 3, 4, 10 carbons, and it is symmetrical. These are the 3 internal symmetrical. Actually, we've got one more. We can take this 3-carbon chain, stop the presses, and do it here. So now that's 3 carbons plus 2 plus 3. We still have one more carbon to add. We can put each of them here. We still have symmetry. This is the 4th internal symmetrical alkyne.